Good day, Math 31s. Today we are talking about Riemann sums. Essentially, we're talking about area under a curve using limits this time. And this is a part 2 of a second part series where last day we were looking at examples maybe as simple as the bottom one here where we had perhaps a function like x squared examining the area under the curve from 0 to 2. So we would be tasked with determining an area by breaking it up into a finite number of strips. So we may have done a right side limit that looks something like this, choosing an arbitrary number of columns and doing an area of each column. Now today we're going to do it a little bit differently, and what we're going to do is approach the area by breaking a shape up into an infinite number of rectangles and then adding them all up. This means the width of each rectangle will be approximately 0. So we're going to start with a pretty simple example, y equals x squared. We'll tackle what the notation looks like and then attempt something that's perhaps a little bit more complicated. So what we're being asked to do in Investigate 1 is find the area under x squared from a equals 0, so sort of a left side at 0, and a b value, a right side, at 2. And as a visual, this is roughly what the last page looked like. So you could imagine if we took this distance from 0 to 2 and broke it up into a certain number of strips. If I said there was going to be 2 strips, we would say the distance of 2 divided by 2. If I said there was 10 strips, it would be a distance of 2 divided by 10, and every strip would be 2 over 10, or a fifth. Now this time, we're not going to actually pick a number of strips. We're going to leave it as a variable. So in our first step, we're going to determine, well, what is the width of each strip going to be? And we're again calling this delta x. So if we want to consider this a formula, we might say that the total width is from B to A, so 2 minus 0, distance of 2, divided by the number of strips. And in this case, we're leaving it as an unknown n, as a variable. So our delta x at this point is going to be represented by a 2 over n. We'll keep this in mind as this width of every strip is at this point variable. Now the second thing we needed after the width, the x value of every strip, was the height. And so in step 2, the height of every strip is based on the input, and x is our input. Now this time I do have this little tiny I subscript, and I represents sort of a counter. And what we're going to do is change this I value as we work our way across to plug in different x values and ultimately create different y values, and therefore heights. So our changing x value, our incrementing x value, is based on our starting x value, which is in this case at a nice 0, and then we're going to add to it our delta x. This time we go up from each strip to the next one. I represents each number. So we start off with the first strip, and then the second, and then third, and fourth, and 5 until the end. And so I represents this counter as we change from one rectangle to the next. So we have some sort of formula for the y value. F is represented by our plugged in value, which in this case is starting with a 0. That's what our a value is in this case. And then we're going to add our delta x attached to this I value, which represents this changing increment. So we're plugging in a 0 plus 2i over n, which is the changing x value, resulting in our x squared, our 2i over n squared, because our equation is y equals x squared. So our last step is to go and look at our final area calculation, which, as a reminder, is this product of our delta x times our f of x. This time, we're now going to examine the number of the sum of n strips as I keeps increasing. So we're going to use a bit of a notation to say we're going to add up, and this is the sigma or sum notation, starting with our first strip. We're going to go until we have an nth number of strips. And again, n is, at this point, variable. So we've got the sum of our y values, which are forever changing, times our width, our delta x, our x values. And this results, in this case, a sum from I equals 1 to n of our y values, which in this case are, just referring to it above, 2i over n squared, times our delta x, which is 2 over n. So we could continue to plug in I equals 1, I equals 2, I equals 3, I equals 4, and keep adding up the terms that are created. But again, when do we stop? If there's 2 strips, 3 strips, 4 strips, whatever n is when we stop. We actually want there not to be just 2 or 3 strips, but an infinite number of strips. So in our next step, we get to examine the number of strips approaching infinity. So our final notation for our area formula, area equals the limit as the number of strips approaches infinity of the sum from I equals 1 to n of, and we actually have a bit of a formula for this specific case happening, where there's a 2 squared times a 2, there will be an 8, I squared, and on the bottom it looks like there's an n squared and an n. This would arrive in an n cubed. So this is the sum of an infinite number of strips of width, basically 0, as we have a n value of infinity. Now, how does this math look? Well, again, we have the limit as n approaches infinity. Not much we can do there just yet, but what we can do for sigma notation is consider there's actually a formula on the previous page for the sum starting with a counter value of 1 to n of either a constant, so a constant plus a constant plus a constant n number of times, like 2 plus 2 plus 2 plus 2, n number of times is 2 times n number of times. If you're having a value of 1, you can say, starting with a 1, going to n, a 1 plus 2 plus 3 plus 4 up until n, where your formula is n times n plus 1 divided by 2, and we saw this last day as our first Gaussian formula. And there's a formula for an I squared plus a I squared plus an I squared as your counter increases, as well as an I cubed, and we are going to be using all of these. So we actually have, in this case, an I squared. We get to only focus on the sum of an I squared and worry about this 8 and the n cubed later. So we're going to pull that out in front of our sum from 1 to n of I squared. And all of a sudden, I'm not asking you to plug in a 1 squared and 2 squared and 3 squared and 4 squared and calculate that manually. What we're able to do is to swap out what I'll put in orange here. We're able to swap this out with a formula from the previous page. So we result in the limit as the number of strips are still going to be infinity of 8 over an n cubed times, and here's the part in orange, the sum of I squared. If we look at the previous page and swap it out, there's an n times an n plus 1 times a 2n plus 1, all divided by a 6. And that is a formula that we sort of accept to be true. This is what we get to evaluate. Now, the good news about attempting a question like this is we've already done this in 2 previous units. I'm going to expand the top, and if we do that, we're going to have maybe an 8n distributing into an n plus 1. So we'll keep this a little bit tidy. An 8n squared and an 8n, and there is on the top going to still be a product times a 2n plus 1, all over a 6 and an n cubed. Lastly, we can tidy up the top, and with our 4 arrows of distribution, we would end up with a 16 n cubed plus a 24 n squared plus an 8n, all divided by a 6n cubed. Now this might look familiar. I asked a question like this in chapter 1, limits as n approaches infinity. I also asked this question in our curve sketching unit. What is your horizontal asymptote as x approaches infinity? But ultimately what we're able to do is divide top and bottom by an n cubed. What would result is a balance of powers resulting in a 16 over 6 as our final answer for this either horizontal asymptote or limit. So 16 over 6 is our answer. Maybe dividing by 2 giving us an 8/3. This is the area under y equals x squared from 0 to 2. An exact answer. We didn't actually have to draw strips. We used something called Riemann sums. Eventually, when we approach these questions, all we're going to focus in on is what is the power on the highest, what is the coefficient on the highest power, and there would have been a 16n cubed, and I wouldn't have really had to worry about all this stuff. That becomes our approach. Let's attempt this once more and see if we're able to confidently move into some practice. So, this becomes our formula. The limit as n approaches infinity of the sum from I equals 1 to n of our counter f of xi times our delta x. And again, this is still a length times a width. A y value times our width. So let's go through our step 1, our step 2, and then create our area in step 3. In step 1, we're asking what is our delta x? And if you want to consider this as a formula, we're really looking at the width on the top, maybe a b minus a, divided by the number of strips. And in this case, we're going from a 1 to a 4 of some visual that we're maybe not super confident in unless we take some thought and put it into sketching. So we do know that the width goes from a 1 to a 4, so a distance of 3 over n. This becomes our delta x, a width of 3 divided in an n number of strips. Not so crazy. Determine the height based on xi. So question is, what is xi? And then we can plug it into f of x. So what is our changing x value? Well, as a bit of a formula, again, we can start with our left side, which is 1. And then we're going to go up by our width and keep changing that width by 1, 2, 3, 4. So our x value that we plug in starts at a 1 and goes up by a little width each time. So for this specific example, we're starting at a left value of 1 and going up by our I counter of width 3 over n. So this is the changing x value, which means we can go to our f of xi and plug this expression for xi into our equation. Our equation is an x cubed plus an x. Our input is a 1 plus 3i over n and a 1 plus a 3i over n. That's your y value. That's your delta x. And we get to go into our area and go back to our formula for area. So, area is the limit as the number of strips approach infinity of the sum from I equals 1 to n of f of xi, which we just figured out was a 1 plus 3i over n cubed plus 1 plus 3i over n. So there's your y value, f of x, multiplied by your delta x. If you can create that, the rest of it is algebra that feels at times slightly tedious, but is a little bit more impressive mathematically than we're maybe used to. So, what do we have to do? Expand this to make it a little bit more tidy. Now that requires a little bit of work because we do have a binomial to cube. And if you've gone through Math 30-1, you might be able to use some Pascal's triangle and the binomial theorem to make that more possible. Otherwise, we have to do this a longhand. So we do have the limit as n approaches infinity of the sum from I equals 1 to n of, deep breath. If you really, really wanted you're more than welcome to take your time and say 1 plus a 3i over n times a 1 plus a 3i over n and a 1 plus a 3i over n. So multiply the binomial times itself 3 times and distribute 4 arrows, 1 plus 3i over n times a 1 plus a 6i over n and a 9i squared over n squared. In our final distribution, now speeding up this a little bit, we would end up with a 1 plus 6i over n plus a 9i squared over n squared, a 3i over n, an 18i squared over n squared, and a 27i cubed over n cubed. We'll keep this on the side, and we'll tidy this up in here and write all that out, multiplied by a 3 over n. So again, this is the tedious algebra part, but again, works out very, very nicely in the end. So as I was saying, once we add those together, we have a 1 plus 6i over n and a 9i squared over n squared plus a 3i over n, an 18i squared over n squared, a 27i cubed over n cubed. There's also this 1 plus 3i over n that I haven't really talked about just yet, and this is all multiplied by a 3 over n. There are some like terms, an I over n, an I over n, an I over n, some n squared, some I squareds. So in tidying that up, we have a 2 plus a 12i over n and a 27i squared over n squared, a 27i cubed over n cubed, all multiplied by a 3 over n. And we'll continue our notation of the sum of n terms, making the number of terms approach infinity. Almost our last term, we get to distribute the 3 over n in and give us a 6 over n and a 36i over n squared and an 81i squared over n cubed, and lastly an 81i cubed over n to the 4. Sum from 1 to n of an infinite number of terms. We get to now apply this sigma onto every one of these factors. And so we're still going to consider the limit as number of terms approaches infinity, but this time we get to say, what's the sum of 6 over n? What's the sum of 6 over n? What I do notice, though, when I write this is that there's no I in there, and that I is the only thing that we really need to consider. So I'm going to take this 6 over n and write it out in front and leave us with a 1. So this is our first term, and then we have the sum from 1 to n of 36i over n squared. And again, I'm going to write everything that isn't an I out in front, because it really is just a product. And another sum, this time of an 81 over n cubed with an I squared from 1 to n. And again, last term, we have the sum of an 81i cubed over n to the 4, which gets swapped out with formulas. So we still have, again, limit as n approaches infinity of a 6 over n. And how do we swap out the sum from I equals 1 to n of 1? If c is a 1, we've got 1 plus 1 plus 1, n number of times, we have 1 times n. So we have the sum of 1 is n. That's quite convenient. And then we can go on to our next term and look at the sum of I. So there's this 36 over an n squared hanging out. And the sum of I is an n plus 1 over 2. n plus 1 over a 2. And we go on to our 81 over n cubed, this time swapping out an I squared sum, which is an n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1 over a 6. And the very, very last one, deceptively not as lengthy, 81 over n to the 4 multiplied by an I to the 4, this time an I to the 3, written wrong, I to the 3. The sum of an I cubed is the last one, n squared, n plus 1 squared over 4. n squared, n plus 1 squared over a 4. There's no sigma notation left anywhere. All that's left is to evaluate each one of these terms. Now the good news about this first one is the n's cancel and we're left with a 6. In the second term, we get to consider the shortcut of saying, what's the coefficient on the highest power? There is a 36n squared that would result. 36n squared. On the bottom there's a 2n squared. So there's going to be a 36 over 2 balance of powers, or an 18. For our third term, looking at the top, there's 81, there's an n, and a 2n. At some point those will come together into a 162 n to the power of 1, 2, 3. 162 n cubed. On the bottom, there's a 6 n cubed. Again, both n cubeds, coefficients balance to give us 162 over a 6. And that does reduce down. In our very, very last term, there is going to be an 81 n squared, eventually another n squared. There is an 81 n to the 4. On the bottom, a 4 n to the 4. So eventually, your coefficients of 81 over 4 work out nicely. And again, we've now evaluated the limit of each of these. And you could add together your 6 plus 18 plus 162 over 6 and an 81 over 4. And saving that for a moment of vision would be your final answer for the area under a quite complicated function x cubed plus x from a 1 to a 4. And this is Riemann sums.